Hello everyone, my name is SDCF and today I would like you to present a paper from HotEdge 2020 called SAFACE towards scenario-aware face recognition via edge computing system. And here is a table of contents of this presentation. Let me start with background and motivation. Here is the basic face recognition flow. First, you need to train your face recognition model on particular dataset. And in standard surveillance system, there is a face detection process and face alignment. Once you detect the face, using the face alignment algorithm based on facial landmarks, you will align the face. And step number 3, you will feed the probes into the face recognition model. And then you will, the model will extract the face representations. And the last stage will be the comparison and determining the identity of the person from the existing gallery. But there are some challenges in face recognition system. So when you build your face recognition model, you train it with static datasets. But in reality, there's a vast variance between training data and real-world scenario data. Such issues like head poses, illumination, different visual quality, and other factors may highly influence the performance of your model. So the question is how to build a robust face recognition system. Well, we can collect more training data from the target scenario and then fine-tune the face recognition models. But there are some problems with this approach. First, we need to label the training data, which is labor intensive, and second, actually this kind of approach will not scale in practice because we may get the thousands of different faces every day, and manual data labeling will be just a headache. So the authors proposed their solution called the SAFACE system, and they use unsupervised online learning to adapt to targeted scenarios so that they solve the label intensive work, because there's no need to label. The system will perform the unsupervised learning. And second, they leverage edge computing paradigm to solve the scalability issues, so that their system will perform the online learning itself, and in addition, it will do the inference too. So now let's have a look how exactly they implemented the unsupervised online learning. Unsupervised online learning algorithm is based on triplet loss described in this paper. So and here is an example of triplets generation. So we have a face tracks from the last layer of our architecture on the cameras, and we pick the first frame of the scene. And for each example, we do as follows. So we pick this example and mark it as an anchor, and that means other examples will be negative samples. And using the feature distance, we find the example that has the minimum distance to our anchor, and so we mark the first item in our triplet as anchor. Second will be the example that has the minimum distance, and then we need to find the positive example on the same track of the anchor that has the maximum distance. So at the end we'll have positive example, negative example, and the anchor itself. And using the triplet loss, we will perform the learning process. This unsupervised online learning algorithm will be used in SAFACE system. This is the SAFACE system workflow. So basically, we can divide this workflow into 5 steps. Okay, first, the model pre-training. So as I mentioned before, we have training datasets, and using these datasets, we create face recognition model, we train it, and then we have face detection and face tracking stage, where in surveillance system from video sequence we extract the face tracks, and after that we perform the actual face recognition inference. So using the face recognition model, we do the inference, step C, to get the result, and at the same time we do the triplet generation. Here we have a triplet, face triplet, and the last stage will be the online learning using the face triplets. Basically the same face recognition model at one time just does the inference process, and at another particular time, scheduled time, is going to do the online learning. About what is scenario shared and scenario aware part of the face recognition model, we need to understand the system architecture first. So this is the SAFACE system overview. So this is the 3-layer architecture, and here is the top layer where we do the initial model training using the powerful cloud servers, and the face recognition model that was created and was trained will be further delivered to the next layer or middle layer. Here we have the edge servers, multiple edge servers that will be located into different places and will be responsible for different scenarios. And in this stage we do online learning, context-aware scheduling, and face recognition. So context-aware scheduling will be responsible for whether to do online learning at particular instance of time or to do the inference. And the actual face recognition will be done on edge servers. And the bottom layer will be our IoT devices or smart cameras, and they are powerful enough to do the face detection, face alignment, and tracking. So basically all these face tracks will be delivered from the bottom layer to the edge servers. These smart cameras will be located in different places, therefore they will have their own target scenarios. And the question is how the actually the edge servers will adapt to this particular target scenario. And here comes our face recognition model with scenario shared and scenario aware part. So when the cloud server generates face recognition model, it provides this model to all edge servers. And all edge servers will have a scenario shared part. However, using their fine-tuning technique, they will adapt to a particular scenario and will fine-tune or update scenario-aware part of the model. Therefore, each edge server will have its own adapted face recognition model. Even though their scenario shared part of the model will be same, their scenario-aware part of the model, so we may say the last layers, CNN layers, will be scenario-aware and will be fine-tuned according to the target scenario. So as I mentioned, inference and learning processes need to be performed on the same edge server, and the context-aware scheduling will be responsible for this. So we have two cases here. Case number one, where there are lots of faces to be recognized on the same frame, or we can say the same scene, and not too many. And we have here edge server, and as you may see, based on the load, based on the number of faces to be recognized, the edge server is busy or idle. So if edge server is busy enough, the small batch for online training should be provided. However, when it's idle, where not too many faces on the scene, we may provide the larger batch for the training. And this is exact way they calculate the batch size. But first we need to understand the annotations. So NC, this is the maximum number of cameras in one edge, and NP max is the maximum number of probes contained in one frame, and NE maximum number of probes that can be processed in one time interval. So this, which is equal to number of cameras times number of probes in the frame, and it should be greater or equal to a maximum number of probes that can be processed in one time interval. So to calculate the optimal runtime batch of online learning, they created this formula where Bmax, this is the maximum batch that edge can take, and alpha, this is coefficient to adjust effective computation utilization. So they claim that this alpha, this is the hyperparameter, and it needs to be adjusted for particular edge for certain scenario for the better utilization. Now turn to evaluation process. In order to simulate the real environment, they created a prototype. So this is three-layer architecture, and for the first layer, or in order to imitate the cloud servers, they employed one cloud machine, uh, which has the GPU server with 4 GTX 1080 Ti and powerful processor. So in cloud server, as you remember, we do the model training, and for the edge servers, they use one edge server desktop PC with one GTX 1080 GPU and pretty good processor. And for the last layer or bottom layer, the smart camera IoT, this is the high silicon, high 35 camera, and it has two ARM processors, so it has enough processing power. And all these are communicated using TP-Link router and 100 megabits per second LAN. So this is their prototype they built for experimentations. And the next thing is dataset. Authors used private dataset from surveillance cameras, and here we have scene 0, the camera which is located closer to the face or human faces, and scene number 1, where the camera is located in a higher position. So we may see we have two different scenarios here. Unfortunately, yeah, like as I mentioned, this is the private dataset, and the authors couldn't reveal the faces. That's why they are hidden. Important thing to note here that test set was labeled by people, whereas the training set uh, used by unsupervised online algorithm that was mentioned before, and the training and test ratios are 5:1. Let's talk about the experiments. So first experiment they did was devoted to check whether we have the accuracy improvement with online learning. So they used three pre-trained models on static datasets, and they evaluate them on scenario 1 and scenario 2, and showed the uh, results before online learning and after. So as you may see here, in all cases, the online learning was beneficial for them to increase the face verification or face recognition accuracy, even though the percentage is the improvement is not so high. um, in all of these cases, it shows that unsupervised online learning works, and the model adapts to a particular scenario better. Next experiment is to show the partial fine-tuning speed and accuracy trade-off. So we have two scenarios here, and here the y-axis shows the speed up, and x-axis shows the layers you start fine-tuning with. So basically, the graph shows that the more layers you train, higher accuracy you're getting, but you're losing in speed up. However, less layers you train, you're getting more speed up of training, but the accuracy is lower. And this kind of trade-off can be seen in both scenarios, and it's important to pick proper layer for fine-tuning. And we have last experiment to show how different strategies of online learning, in particular context-aware scheduling and fixed batch strategy, influence to the inference throughput. So we have here fixed batch sizes in x-axis and inference throughput in y-axis. And having particular fixed batch size here gives us 38.52 throughput or triplets per minute for the inference. However, if we apply dynamic strategy, we achieve higher throughput, 51.03 at inference. And overall, the experiment shows that dynamic strategy improves the throughput of the inference process for 32.4% rather than fixed strategy. So in conclusion, face recognition system is proposed, so it takes information from live video to perform unsupervised online training and face recognition inference at the same node. And it deploys the algorithm on flow on edge computing system rather than on centric cloud. And it shows efficient execution of both face recognition, inference, and online tracking tasks with runtime scheduler. And the system improves performance of the face recognition model according to real environment of target scenario. And results indicate that dynamic context-aware strategy in SAFACE can achieve better inference throughput, having a high training efficiency. So 32.4% improvements in comparison with fixed strategy. And in my opinion, this is the way we can improve this paper. First, we need to make experimentations with different scenarios, not only two as they presented. So we can use different angle views, camera setups, and lighting conditions. And I think we need to enlarge product architecture, not just one camera, one edge, and cloud server, but in order to imitate, we need multiple cameras connected to multiple edge servers. And there should be clarification of data, because not much information provided about the training data set that use like duration of the video, number of samples, and conditions that are present in the video. And I think they have to show the sample examples. Of course, due to the privacy, faces are hidden, but it's important to take a look at the real samples. And it would be great if they would make the comparison with existing works, because there's no comparison with a work of its kind. And here I summarize the paper evaluation in this slide, so you can take a look. I believe that paper has a practical importance in the industry and addresses the common issues. However, I think we need more experiment with various scenarios and to have enough information about data, and it would be nice to have a comparison with existing techniques. So thank you very much for your attention. Please ask your questions. I will be happy to answer them.